Number 6. Okay, so we have x squared plus y squared is equal to 25. dy over dt is equal to 6. And we're supposed to find dx over dt when y is equal to 4. So as it turns out, this is basically just a simple problem of differentiation. So if we take derivatives in both sides with respect to t, we're going to have what? Two x dx dt plus 2y dy dt equals 0, right? Since the derivative of 25 is just 0. So now all we have to do is put in what we know. So it'll be 2 times 3 times dx over dt plus 2 times 4 times 6 is equal to 0. How did I get 3?
Don't you plug it back in somewhere? Where do you do that?
Yes, well remember our original equation is x squared plus y squared is equal to, and I'm going to cheat here and I'm just going to say it's 5 squared. Y is 4, so 3, 4, and 5 are the Pythagorean numbers. Right? If not, obviously you can solve for x. Alright, x squared is 25 minus y squared. So x squared is 25 minus 16. So x squared is equal to 9. So x is equal to 3. Right? Technically, I should point out that for all of these problems, x actually should be plus or minus 3. Right? But in reality, we're usually assuming it's positive, because we're talking about like positive distances. So, anyway, dx over dt is minus 8. Is that making sense? Okay, what else? 14. Yeah, that's one of the problems we haven't actually done yet. The last problem I did was 13, right? I did 19 too? Oh yeah, I didn't finish it. Okay, so you need me to do 14? What are your homework, by the way, problems? Because I don't remember. Okay. So 14 says the following. And remember what I told you about these types of problems. Basically, the most difficult part about the problems is to actually get to the equation that relates all the terms together. Because once you get there, all you have to do is just implicit differentiation and plug in all the values you know. So the only difficulty is to actually set it up. So, a spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight toward the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building. Okay, remember what I told you. As a first thought, just read out the problem and kind of get a feel for what we're looking at. Second thing we should do is actually draw a picture of what we're actually more or less looking at. So we have a spotlight on the ground that shines on a wall. A man walks from the spotlight to the building, and we're looking at it at his shade, right? So it will only make sense to have the spotlight, let's see, and then we have this lovely wall over here. So the man is walking from the spotlight to the wall. Does that make sense? Okay. So a spotlight on the ground shines on a wall 12 meters away. So if I am to use some coloring here, I would have that orange line to be 12 meters, right? Okay. What else we have? If a man 2 meters tall walks from the spotlight toward the building, so man 2 meters tall, he's 2 meters tall. How many feet is that, by the way? I'm 5'11" and I'm 1.8 meters. So it's close to 7. Okay. Walks from the spotlight towards the building at a speed of 16 meters per second. Right? How fast is the length of his shadow of the building decreasing when he is 4 meters from the building? Okay? So the shadow is decreasing, the distance is decreasing from the building. So now the question is, what should our variable be? And it doesn't necessarily have to be this way. I'm just going to choose it this way. I'm going to denote this particular distance to be x. Okay? So what does that tell us about the problem? It says a man walks from the spotlight towards the building at a speed of 1.6 meters per second. How can I relate that in terms of x? dx over dt is equal to negative 1.6 meters per second, you say? Remember what I told you last time. We always had the rates of change positive because we were always assuming that the things were increased, the distances are increasing. In this case, x is getting smaller. Because x is getting smaller, the rate of change of x is negative. Does that make sense? If I would have denoted this distance to be x, then my rate of change would have been positive. Is that making sense? Okay. So, how fast is the length of his shadow on the building decreasing when he is 4 meters away from the building? How should I represent that? Well, let's use this color that I can never remember what it's called. If I draw one of those lines, if this distance is y, sorry, what am I looking at? The length of the shadow. Oh, never mind. Wrong picture. So if I do that, then what I'm looking at is, if this is y, then what I'm interested in is dy over dt is equal to what? When x is equal to 4. Does this make any sense? Yes? Okay. So we wrote everything the problem gave us. Now, how do we relate x and y?
Is it 12 minus x?
12 minus x just gives you this piece. So let's forget about the actual drawing that I had. If I am to draw two triangles, and I probably chose x the wrong way. But anyway, what do we know? This is y. This is 12. Right? This is 2. And this piece is x. Right? So then this piece is 12 minus x. Right? And if I label these A, B, C, D, and E, the triangles, triangle ABC and triangle ADE, are similar. Geometry. That tells you that 12 minus x divided by 12 has to equal 2 divided by y. Yes? Remember, similar triangles have have the same proportion between their sides. I haven't looked at the hypotenuse because it doesn't actually play any role in my problem, right? So there's really no reason to go necessarily there. Is this making sense? Yes? Okay, so how do we solve this? So how about we write this in a simpler version? How about we write it as 1 minus x over 12 is equal to 2 over y. Okay? So now, what happens if you take derivatives in both sides with respect to time? What do you get on the left-hand side? That was a question. Negative 1 over 12 dx dt equals negative 2 over y squared dy dt. Does that make sense? Remember, this is one of those derivatives that I said I'm not going to spend because it's, the derivative of 1 over x is minus 1 over x squared. Right? Remember that? Okay? So now all we have to do is figure out stuff. So, what are we solving for? dy over dt, right? So dy over dt is going to equal y squared over y squared over 24 times dx dt. Does that make sense? Yes? For those of you who are still awake? Or that actually woke up? Still awake or woke up? Which one? Woke up. Is this making sense? Multiply by negative y squared over 2. You need to get dy over dt by itself. So you either divide by this whole quantity or multiply by its reciprocal. Yes? Okay. So now, what is y squared? Because dx over dt we know. So what is y? And the answer is we don't know. 12 minus x over 12 is equal to 2 over y. Right? X is equal to 4, which means 8 over 12 is equal to 2 over y. Right? Which means y is equal to 3. So dy over dt is equal to 9 over 24 times 1.6 meters per second. Right? So let's see, dy over dt equals 9 over 24, that's 3 over 8, right? And 1.6 is just 16 over 10 meters per second. So 0.6 meters per second. Yes, it should be negative. Oh, the reason why I have it wrongly is because remember, dx over dt is minus 1.6 meters per second. I forgot about the minus, from minus 1.6. Is this making sense?
Yeah.
Okay. What else? Number 18. Again, the idea is the picture. A boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching? And you have the picture. So basically, I'm not going to draw that picture, but basically what you're looking at is you're looking at a triangle. And what do we know? That side is 1 meter, right? And now if I call this x and this y, what do I know? dy over dt is equal to 1 meter per second, right? What do we need to find out? Dx over dt when x is equal to 8. Very good. And that's all there is to it, right? I'm hoping everybody can connect x and y. It's a theorem starting with P. Yes? Okay. What else?
Can you set up 16?
16. A baseball diamond is a square with a side of 90 feet. A batter hits the ball and runs towards first base with a speed of 24 feet per second. At what rate is his distance from second base? So, what we need to do is we need to draw a lovely diamond, right? That's a diamond. First base all of a sudden became much farther away than the other bases. Okay, so a batter hits the ball and runs towards first base with a speed of 24 feet per second. At what rate is his distance from second base decreasing when he's halfway to first base? So what are we looking at? If my person's right there, let's call it E, right? we're looking for this particular distance, right? Maybe I should have written home plate, first, second, and third. Does this make sense? So if this is y and this is x, what do I know? What is dx over dt? Negative 24 feet per second. Right? What else do we know? We need to find dy over dt when x is equal to 45. Does that make sense? Remember what I told you. Pretty much most of these problems will come down to the Pythagorean theorem. That's pretty much what you're going to be looking at. Yes? The runner is halfway to first base. And it's 90 feet in between bases. Is this making sense? So now, I guess tonight when you watch the MLB playoffs, you can figure out if the second baseman has enough time to throw the person out on first base or not. Or okay. And you should not have problems setting up part B as well. Part B is in relation to third base. Does that make sense? So if I label this Z, then you're looking for dz over dt. And based on the nature of the problem, dy over dt should come out to be negative, and dz over dt should come out to be positive. Does that make sense? Because if you think about it, your distances, as x goes from home to first, y is going to get smaller and smaller, but z is going to get bigger and bigger. Right? The question is what happens. It's exactly at the moment where you're halfway between first and second, between home and first.
Oh, so say what happens when you get to
As soon as you start moving from first to second, dz will increase. It will decrease. Yes. Okay. Does that make sense? Yes.
If we get, do you want to just leave them like that?
Sorry, say that again.
Not a perfect square. Just leave them
In radical notation? Yeah.
Number 18, I think.
Yeah. When x is 45, y is 45 square root of 3.
so leave it that way. So just
Why do I know it's 45 square root of 3? This is one of the trigonometric triangles. This will be a 60-degree angle. That's a 30-degree angle. Technically, you're looking at 1, 2, and square root of 3. Okay. Anything else?
For number 10, did it just come out? Was it a square root answer? Was the answer and you added? Or did that just mess up?
I would have no idea.
Alright. So like 250,000 plus 19,000.
Yeah, it probably will be square root, because if you take 4 times 35, that'll give you 140, which is not a nice number. And then the other one is just 100. No, because it's 25 kilometers per hour times 4.
Is it 120? Is it 125 or 25?
You're only going 4 hours, not 5.
You're going 4 hours. 4 times 25 is 100. But remember, this is very similar to the problem that I set up.
I just heard that from 125.
19, I think, right? Yeah, when they're actually far away, when they start moving. But out of curiosity, because I wanted to do this last time and I never got around to it. How about number 15? And I'm just curious to see if you know how to set it up or not, more than anything else. It says a man starts walking north at 4 feet per second from a point P. 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due west of P. At what rate are the people moving apart 15 minutes after the woman starts walking? Okay, so how do we set it up? First things first, we read the problem. Let's draw a diagram. It seems that they leave from 2 points to 2 different points, right? So let's figure out what those points are. So if I start with a point P, the woman starts walking 500 feet east of P. So if this is P, and then this is Q, then this is 500 feet. Right? The man is walking north at 4 feet per second. So if I label this x, then dx over dt is equal to 5 feet per second. 4. The woman starts walking south at 5 feet per second. Okay, I'm running out of picture space over here, so let me draw it again. This is P, this is Q, this is X, this is going to be Y, 500. So dx over dt is 4 feet per second, dy over dt is 5 feet per second. And what we're asked is, what is dz over dt? So would you know how to set it up?
You have to find out how far the open is after 15 minutes.
We have to find out where both of them are after.
But then you just kind of move the triangle. Make it bigger.
Yeah, but it doesn't matter. So remember what I said last time. If we connect and make it a large triangle, then this is going to be 500. This is x. So z squared is equal to the quantity x plus y squared plus 500 squared. Does that make sense? Yeah? So now what is x and what is y? Because obviously take derivatives both sides, hopefully you know how to do that. The bigger question I think would be what x is and what y is.
That is the rate times.
Okay, so what is y?
5 feet times 15.
5 times 60 times 15. Yes? What is x? 4 times 60 times 20. Does this make sense? Yes? So two things happen here. First of all, the man started moving before the woman, right? So the woman started 5 minutes later. So the man walked for 20 minutes. The woman only walked for 15 minutes. The other thing that you have to keep track of is you have to make sure that your units actually make sense. The rates of change are in terms of feet per second, yet they walked minutes. So you have to multiply by 60 to bring back everything to seconds. Does that make sense? Yeah? Okay, so obviously your answer should be in terms of feet, right? And if you write out all the numbers, it should come out as feet. Yeah? Okay. All right. Are we done with this section, or do you have more questions? Okay. I'll take that as a we're done. So remember, if we have a function y equals f of x, and you're looking at the equation of the tangent line, at a point A and f of A. Do you remember what it is?
F prime of A.
F prime of A times x minus A. Right? So everybody remembers that? That's the equation of the tangent line. I mean, I would assume that we've done so many so far. That's a big assumption. Okay, from here, y is equal to f of A plus f prime of A times x minus A. So the idea is when x is close to A, f of x is approximately equal to f of A plus f prime of A times x minus A. This is called the linearization of f of x, and is denoted by capital L of x equals f of A plus f prime of A times x minus A. So now that I wrote this, I actually haven't explained anything about it. Do you understand what we're actually saying here? Remember the equation of the tangent line. Remember what tangent lines do, right? They touch the graph in one particular point, right? And remember what happened when we talked about tangent lines. As you get closer and closer to that particular point, the graph and the tangent line are basically going to be almost exactly identical. Okay? So the idea is, if you have a function that's relatively ugly, but you want to figure out approximately what the value of the function is, you can use this linearization. Why is it called linearization? Well, because again, remember what the tangent line is. It's a line, right? The only variable here is x, because f prime of A is just going to be a number. This is a number, this is a number, that's a number, so you only end up with a linear function. So even though your function could be very ugly, your linearization is just going to be a linear function. Is that making sense? So, as a question, for instance, what happens if you want to guesstimate the square root of 3.98. Calculator. Of course, calculator. Okay. Well, here's the idea. How about if you look at f of x equals the square root of x plus 3. Bless you. Can we come up with the linearization of f of x? Again, that was a question. So, what do? We find f prime of x. The linearization at, I should say, x equals 1. Because without actually saying what point, you can't actually come up with it, right? So f prime of x is 1 over 2 times the square root of x plus 3. So f prime of 1 is equal to 1/4. And we know f of 1 is equal to 2, right? And so your linearization is going to be 2 plus 1/4 times x minus 1. Right? Or if you want to work the algebra, x over 4 plus 7/4. So now,
How do you like us to? Do you want us to solve it out?
no, it doesn't matter. But you need to actually, the whole goal is at this point is to actually try and approximate that square root. That was basically what we started with. So, what would you guess the approximate value of the square root of 3.98 to be? Yes.
0.98 over 4 plus
0.98 over 4 plus 7/4. Does this make sense? Yes or no?
Is there any time we use a value of x then?
Oh, yeah, I mean, the only reason why we actually chose one, first of all, this is an example in the book, but the only reason why we chose one is because if you put in 1 for x, you get square root of 4, which is 2. So you get a nice round number.
Is that also just close to the square root we're trying to find?
Yeah, the closer you are to the actual point you're looking for, that's basically the more accurate the problem is. So, anyway, if you compute this, you end up with 7.98 over 4, which is 1.995. So anyway, I'm not going to spend too much time talking about linearizations. They're not necessarily I'm not going to put too much effort into this. You might ask yourselves, what exactly is this the point for? And what exactly is the benefit of doing this? And as it turns out, this function is not necessarily ugly, but many times you have really, really ugly functions. And you don't necessarily want to find out the exact value, but you would like to actually be close enough to something. So, in doing this, you can easily come up with relatively close values to what you're looking at and kind of get an approximation. What people do is they actually use computers or calculators to come up with these values. And yes, for this particular problem, you put in the square root of 3.98 in the calculator, and it'll tell you exactly what the value is, right? But this is just an example. It's a simple example to show you how it works, not necessarily that this is a real life example that you're going to come up with. I mean, you can come up with some functions that are really, really ugly that you're not going to be able to graph or evaluate functions that easily for. And this way you can actually get a relatively good feel for things. Okay. The other thing that we're going to talk about in this particular section is called differentials. And the funny part about differentials is that we spent a lot of time, or I spent a lot of time talking about the fact that dy over dx. So if I say y is equal to f of x, then dy over dx is equal to f prime of x, right? And I spent a lot of time talking about the fact that dy over dx is just an actual symbol denoting the derivative, right? Well, not anymore. The differential says that dy is equal to f prime of x dx. Which basically says take the derivative and just write a dx next to it. Okay?
Till dx equals.
So you might ask yourselves, why exactly are we doing this? And to answer your question, we're going to find the answer in about 5-6 weeks when we talk about integrals. This is actually when it shows up when you talk about integrals. And we're going to look at it. When we talk about integrals. So anyway, if you look at your homework problems, you have a whole 3 problems to solve for this homework. You have problems 2, 4, and 18. 2 and 4 ask you to find the linearization of a function, and 18 asks you to find the differential of the function. So how about we do 17 so you see how things work. Okay, so 17 says the following. Part A, y is equal to x squared times sine of 2x. And so the question is, what is dy? 2x sine of 2x That's why I put the 2 in front. Multiplied by dx. That is it, yes.
Where did you get the
The x squared it's a product rule. The derivative of the first times the second plus the derivative of the second. So what's the derivative of sine of 2x? Cosine of 2x times 2. Chain rule.
You do product together.
Product rule with the chain rule, yes. Is this making sense? Should I do part B as well, or? Y is equal to the square root of 4 plus 5x. So dy equals, by the way, one of the reasons, I didn't assign too many problems because I don't want you to spend too much time on this, like approximating or anything like that, because it doesn't necessarily play a role later on in the semester. But what I would like to know is that later on, if I actually say what is the linearization of a function, you know what actually that is. Or if I say find the differential, you kind of have a feel for what the differential is. Not necessarily that, approximate the square root of 3.98 or whatever that the, situation may be. Okay, so what is dy? Five over 2 times the square root of 4 plus 5x dx. Does that make sense? Yes? Okay. Questions about this? Okay, so we're going to start talking about chapter 3 then today. And it's more or less kind of by design. I have set up that on Monday we're going to talk about sections 1 and 2, which may or may not have been, feasible, since there's a lot of stuff to talk about. So chapter 3 deals with, we're going to look at exponential functions, exponential functions, logarithmic functions, inverse trigonometric functions, and their derivatives. So to start off, section 1 deals with exponential functions. Okay. Now I know we technically tested you on exponential functions in the pretest, but we all know how wonderfully good everybody did on the pretest. So I'm going to more or less assume we haven't talked about them that much and just kind of like go over the review of things. So what is an exponential function? F of x is equal to a to the x power. Why is it called an exponential function? Well, because x is in the exponent, right? Remember, powers are called exponents, right? Now this is where I'm going to skip a little bit from section 1, in the sense that in section 1 they actually go ahead and define a to the x rigorously, in the sense that for this to be a function, we need to be able to say what is 2 to the square root of 3, for instance. Okay? We know what 2 squared is, we know what 2 cubed is, we know what 2 to the 2/3 is, or anything like that. But what happens if you actually put in an irrational number? Or what is 2 to the power of e, for example? Okay? And as it turns out, this is where you can approximate things, and I'm not going to spend the time, but you can approximate things using rational numbers. Like e is 2.71, right? Put 2.71, and it keeps going. So technically, if you approximate that with 2.71 and 2.72, right? So the idea is the following. I guess I said I'm not going to talk about it, but let me just say very briefly. Square root of 2, for instance, is 1.4142, and so forth. Okay? So the idea is, if I want to talk about 3 to the square root of 2, well, I can basically approximate that anywhere between 3 to the 1.4 and 3 to the 1.5, which I can evaluate. Right, 1.5 is just 3/2. Take the square root of 3, and then cube that. But I can approximate it also by 3 to the 1.41 and 3 to the 1.42, or I can go even more, 1.414, 1.415, and basically just take a limit of that. The idea is, where are the left values kind of converging towards, where are the right values kind of converging towards, and that's your value. So, that being said, what we're going to say is the following, and this is where, as I said, I'm going to more or less skip a little bit. F of x is equal to a to the x, where a is bigger than, strictly bigger than 0. This is called an exponential function. Okay? What is the domain of this function? All real numbers. Why? Well, let's assume a is 2. 2 to any power makes sense, right? If I look at 2 to minus 1, that's just 1 over 2, so it makes sense, right? As it turns out, and we can talk about this a little bit. So, if a is between 0 and 1, then the graph of the function will look like that. Right? Whatever the value of a is, a to the 0 is equal to 1. Right? So it'll go through that point. Does this make sense? if a is equal to 0, if a is equal to 1, then 1 to any power is 1, so it'll just be a horizontal line of height 1, right? And if a is strictly bigger than 1, then your function looks like this. So far so good? As I said, some of this stuff might be familiar and it might be a little boring. I just want to make sure I'm covering all the bases. So when we start talking about exponential functions and take derivatives or anything like that, or we start describing exponential functions, you at least remember what they are. Okay? So let's look at a couple of things. If a is less than 1, well, clearly bigger than 0, then can you tell me what the limit as x goes to minus infinity of a to the x is? And what is the limit as x goes to infinity of a to the x? Picture is worth 1,000 words. That picture, when x goes to infinity, your function goes to 0. When it goes to minus infinity, your function goes to plus infinity. Does that make sense? On the other token, if a is bigger than 1, then the limit as x goes to minus infinity of a to the x is equal to 0 and plus infinity. Again, picture's worth 1,000 words. Is this making sense? Yes. Uh-huh. Mm-hmm. To the left. X goes to minus infinity means we're shooting this way. Right? Is this making sense? In both cases, what can we say about y equals to 0? It's a horizontal asymptote. Is this making sense? Yes? Okay. All right. We're in calculus, so it only makes sense to actually define things more complicated than you've seen it before. Everybody knows the number e. Well, as I said, this is calculus. So we're going to define the number e to be equal to the limit as x goes to 0 of 1 plus x to the 1 over x. Or, and they didn't give us this particular definition, but I personally like it better. E is equal to the limit as n goes to infinity of 1 plus 1 over n divided all raised to the nth power. Why do I like this better? Because you've actually seen this. If you've taken any sort of business courses or anything related to economics, do you remember PERT? P equals e to the RT. Instantaneous rate of change is in the interest compounded continuously, right? Well, this part was P equals P0 times 1 plus R over N divided all to the power R times T, I think it was, or something like that, right? This was the interest compounded N times a year with the rate of R. And the idea is that if N goes to infinity, which means you compound it continuously, that becomes that. But anyway, besides the point, this is actually how we define the number E. And so the natural exponential function is defined to be f of x equals e to dx, which has a domain of minus infinity to infinity. Can you tell me what the range is? Any thoughts? 0 to infinity. Right? If you take a positive number, raise it to any power, you can never get negative numbers. Right? Graphically speaking, the graph of e to dx will look like that. Right? Since e is bigger than 1. Does that make sense? Yes? Okay. So why don't we look at a couple of problems and see what we can make out of these. Your homework is, I guess, number 10. Make a rough sketch. Okay. So how about we see how this rings any bells? So if I look at problem number 9 on page 147, I will have y is equal to minus 2 to the minus x. And so we're supposed to make a rough sketch without using a calculator. So if I am to ask you for the graph of 2 to dx, do you remember what it looks like? 2 is positive, 2 is bigger than 1, so it'll look like this, right? Does that make sense? Okay. How about if I look at the graph of 2 to the minus x? What happens if you replace x with minus x? Is that what you said? Replacing x with minus x reflects the graph over the y-axis. Do you remember reflections at all? Yeah. If not, just again, think about the following. You have 2. You have a positive number raised to some power. That can never be negative. So you're not going to be here at all. Right? And now as the last, also by the way, I should point out that this is the same thing as 1/2 to the x power. Right? So now what is the graph of y equals minus 2 to the minus x? Second graph flipped over the x-axis. Does that make sense? Okay. That was a hard one. Let's see, what else? 16? Oh, okay. So let's do 15. It says f of x, part A, f of x is equal to 1 over 1 plus e to the x. And the question is, what is the domain of this function? All real numbers? Why? 1 plus e to the x has to be non-zero, right? If it's 0, you can't divide by 0, right? However, e to the x is strictly bigger than 0. 1 plus e to the x is actually strictly bigger than 1. Clearly it can't be 0, right? So since it can't be 0, the domain is everything. Is that making sense? Alright, how about part B? F of x equals 1 over 1 minus e to the x.
Everything except 0. 0.
Everything except 0. Why everything except 0? 1 minus e to the x cannot equal 0, which means e to the x cannot equal 1, which means x cannot equal 0. Right?
Can we write the domain as like all reals x is not equal 0?
Or yeah, or you can say it in words, all reals except for 0, yeah. There's, as I said, there's a variety of ways you can write it. The only thing I will not accept as an answer is that. And we talked about that, right? That just tells you that x cannot equal 0. It doesn't say that it can equal everything else except for 0. Okay. What else? Let's see. 24, 26. Ah, yeah. Number 23. Well, you know, we've been away from limits far too long. The limit as x goes to infinity of 1.001 to the x power. This is a question. What is the limit as x goes to infinity of 1.001 to the x power? It is not 0. It's positive infinity because 1.001 is strictly bigger than 1. Why would this make sense? Well, because if we come back to what I said above, over here, if a is strictly bigger than 1, the limit goes to infinity. If a is bigger than 1, your graph looks like, okay, looks like that. Right? Make sense? Alright, wonderful. How about number 25? The limit as x goes to infinity of e to the 3x minus e to the minus 3x divided by e to the 3x plus e to the minus 3x. Which, by the way, is the hyperbolic tangent of 3x. If you've ever heard of hyperbolic trigonometric functions before. So what is this limit? Well, let's put it infinity for x and see what happens. E to the infinity is infinity. E to the minus infinity is 0. Yes. The limit as x goes to infinity of e to the minus x will equal to 0. Right? Again, think about your graph. E to the minus infinity means you're going this way, so you'll end up at 0, right? So coming back up there, we have infinity minus 0 divided by infinity plus 0. Infinity over infinity is? As it turns out, for this particular problem, it is 1. But it doesn't necessarily have to be 1. Remember what happens when it all depends. Infinity is just a concept, right? The question is which one of these. Again, we can come back to polynomials if you want. We have infinity over infinity. Which one of these infinities actually gets to infinity faster, so to speak? Is the denominator going faster to infinity than the numerator? Then you end up with 0. Is the numerator going faster? Then you end up with infinity. If they both go in the same time or close to the same time, then you might actually end up with a finite number. Yes? This one? No?
Because we're going to infinity this way, and it's like negative x.
This is the graph of y equals e to the x.
So, no. But with that,
It's not this function. What I'm saying is if you put in infinity for x, you end up with e to the minus infinity. So if you think about the graph of e to the x, e to the minus infinity means you're going that way. I figure I'll just show you one graph versus showing you a graph for each of these functions separately. Okay, so how do we solve this particular problem? Based on your tests, we say that and move on? Or you write 0 or 1? As it turns out, the limit is 1. But how do we show that the limit is 1?
It could be minus 0 over it could be plus 0.
What happens if you factor out an e to the 3x on top? What are we left with? 1 minus e to the minus 6x, you say?
Can you explain that?
I'll explain that. Does that make sense? I'll come back to the factoring. Assuming that you believe the factoring is correct, do you understand why the limit is 1? Do you see the progression? Factor out e to the 3x, they cancel out. And now when I put infinity in for x, e to the minus infinity is 0. E to the minus infinity is 0, so I end up with 1 minus 0 divided by 1 plus 0. Bless you. So I end up with 1. Right? Now, let's come back to why is that the case. Let's say I have x squared plus x plus 1. I factor out an x squared. What am I left with?
1
Plus 1 over x plus 1 over x squared. Right? That's what we've done before. But that just means that it's x squared times 1 plus x to the minus 1 plus x to the minus 2. Right? Yes? Laws of exponents. So if I look at e to the 3x minus e to the minus 3x, and I factor out that e to the 3x, I'm left with 1 minus e to the minus 3x over e to the 3x. Which is the same thing as e to the 3x. 1 minus e to the minus 3x times e to the minus 3x. If you want to write it in that way. But the key idea is it's minus 6x. Does that make sense? Yes? Again, that's how laws of exponents work. 27 is a good one. The limit as x goes to 2 plus of e to the 3 over 2 minus x. So any thoughts? Besides does not exist.
0.
As it turns out, it is 0. So good guess. But why is it 0?
Because
What happens when you put in 2 plus in for x? You end up with 3 over 0, right? But which type of 0? Because this is 2 plus, I have 2 minus 2.1 technically, so it's 3 over 0 minus. So the idea is this is just e to 3 over 0 minus, which is e to minus infinity, which is 0. Does that make sense? Sorry?
Would it be 0 plus?
Well, keep in mind that 2 plus means 2.01 or whatever, 2.1. So you have 2 minus 2.01, so you end up with minus 0.01. Does this make sense? Do you understand how this works? Again, if you just write 0 without actually explaining to me why. No, I think I gave you 3 out of 15 for the limits if you got the right answer, but without actually explaining, or because you just was very creative but still stumbled upon the right answer. Okay, how about 29? The limit as x goes to infinity of e to the minus 2x times cosine of x.
nice.
So what is this limit? And again, if you guess 0, you're in luck. How do we solve this particular limit? What should immediately jump at you when you look at this problem? X goes to infinity. I have a cosine. Cosine of infinity doesn't exist. Right? Because it keeps oscillating. How do we handle limits of infinity of trigonometric functions? Squeeze theorem. That's what should jump at you the second you see a limit of infinity and a trigonometric function. So the idea is that minus 1 is less than or equal to cosine of x is less than or equal to 1. Which means minus e to the minus 2x is less than or equal to e to the minus 2x cosine of x less than or equal to e to the minus 2x. This goes to 0, that goes to 0, so the whole thing has to go to 0. Why is this going to 0? Because it's e to the minus infinity, which we showed goes to 0. Does this make sense? Bless you. Now you understand why I actually spent a little time talking about exponentials and if the exponent is positive or negative or what happens here and there, because we end up actually talking about them. Okay, so we'll stop here. Next time we'll actually learn about logarithms. I guess the one thing I haven't done is actually